Hi, my name is Nicholas Espinal. I'm part of Group 8. This is my Chapter 22 quiz, the eighth question, and this is what it asks. A hollow conducting spherical shell has radii of 0.8 meters and 1.20 meters, as shown in the figure. The sphere carries a net excess charge of negative 500 nanocoulombs. A point charge of 300 nanocoulombs is present at the center. The radial component of the electrical field at a point that is 0.6 meters away from the center is closest to. The correct answer was C, positive 7,500 newtons per coulomb. And the way I got to this answer was through the use of Gaussian surfaces and Gauss's law. Uh, so what they give us is three radiuses pretty much. First radius is 1.2 meters. It's the radius of the entire sphere. The second radius is 0.8 meters, which is the radius of the inner sphere or the inner cavity. And the third radius is what they tell us is that the, the electrical field at a point that is 0.6 meters away from the center. 0.6 meters away from the center would be a radius, but that 0.6 meters is actually smaller than R2 that we have here, which is 0.8, which means that this point is actually inside of the cavity. And the only charge enclosed within the cavity is the point charge of 300 nanocoulombs. So we're going to create a Gaussian surface that encloses this charge and has the radius that is the distance of that point from the center, which is 0.6 meters. Using the Gaussian surface, we use symmetry to help us. As we could see, every single dA, which is the vector of area, the vector pointing out of the surface area is parallel to every single vector of the electrical field, meaning that every angle in between the area and the electrical field at some point on the surface is actually going to be an angle of 0. They're going to be completely parallel. And we already know from the flux, that's just the integral of the dot product of the electrical field and the area, which is just the magnitude of both times the cosine of that angle in between them. But we already discussed that that angle is already 0, and the cosine of 0 is just 1. So when we compute this integral, we're just going to find that the flux is equal to the electrical field times the area. And we also find later that, throughout class, that the flux of a Gaussian surface is the enclosed charge in that surface divided by epsilon naught. And we're going to see that we actually have two equations for the flux. One, electrical field times area, and the other, the enclosed charge divided by epsilon naught. The enclosed charge is, again, just the point charge inside the cavity, which is 300 nanocoulombs. And we're just going to convert that to coulombs, which is really just 300 times 10 to the negative 9 coulombs. And we're going to actually equate these two equations. And we're going to see that one side is going to equal the other. The closed charge divided by epsilon naught is equal to the area times the electrical field. Then we have to ask ourselves, what is the area of this Gaussian surface? Well, the surface area of a sphere is what we have. Our Gaussian surface is just a sphere. The surface area of that is 4 pi r squared. So we're going to replace that 4 pi r squared for the A, and we're going to have we have here the charge divided by epsilon naught is equal to the electrical field times the surface area 4 pi r squared, remembering that r is 0.6 meters, and we're just going to solve for E, the electrical field. We're just going to divide both sides by 4 pi r squared, and we're going to have 1 over 4 pi epsilon naught times the charge divided by the radius squared, and that is going to give us our electrical field. We're also going to notice that 1 over 4 pi epsilon naught is really just K. That's another constant that we have. So it's just going to be K times the charge over the radius squared. And that's going to be equal to our electrical field. They gave us K. It's 8.99 times 10 to the 9. newtons times meters squared over coulombs squared. One of the coulombs is going to cancel, the meters squared is going to cancel, and what we're going to be left with is newtons per coulomb. That is the unit for electrical field, so we know we're in the right direction. And when you compute all of this math here, it's just going to be 7,491.67 newtons per coulomb. And it just asks us which is closest. Answer choice C is positive 7,500 newtons per coulomb. And through the use of Gauss's law and Gaussian surfaces, we're able to find that answer. Thank you.